Hi, everyone. So today we are going to be looking at part two of our lecture on energy generation. And if you recall, in part one, we started with some basics. We looked at what electricity is, how it is produced, how it's distributed, and then we looked at some conventional energy sources for electricity, right? Most of them are fossil fuel based, coal, natural gas. We then briefly touched on fuel oil, right? Because when we're talking about energy, it's not just electricity, but it's also fuel that we use, particularly to power vehicles, right? And we said that is oil based, and that is a huge portion of the energy that we consume. And that leads us now to part two, which is where we're going to focus on renewable energy, right? And this is where, hopefully, this is where we go in the future, right? We're talking about why renewables. I think we have seen in the series of lectures that we already have that it's important that we decarbonize our energy sector to address climate change, right? We talked about climate change and the effect that greenhouse gases are having on our climate and our environment, right? And it's essentially an existential threat, climate change. It has drastic effects. So we do have to, if we want to mitigate the worst of those effects, we need to really decarbonize or stop emitting carbon dioxide and other greenhouse gases. But it's not just those gases; it's also the other harmful air pollutants that we saw way back in the beginning of this course, right? Those criteria pollutants that we talked about, those other hazardous air pollutants that all are associated primarily with the burning of fossil fuels. Right? So there's incentive both from the climate change and from other aspects of air pollution to get away from that as the main means by which we are generating electricity or energy. And there's also a national security interest, right? The more we are dependent on fossil fuels that are at least not produced in the US, right? And now we are somewhat more energy independent right now, but we're also linked with the global economy. So even though you can take the example of Russia and what's happening right now with Russia and the sanctions against them due to their invasion of Ukraine, even though we don't buy much or import much oil from Russia, a lot of the other world does, right? And this is a global market. So by the mere fact that the rest of the world utilizes oil from Russia, by sanctioning them, it's going to have drastic effects on our oil prices like we're seeing right now. And this can affect a whole host of things besides just what we feel in our pockets, right? This can affect political influence and geopolitical influence and et cetera. So there is a national security interest to being energy independent, and a great way to do that is to utilize renewable energy. So in this lecture, we are going to look at the main types of renewable energy: hydroelectric, biomass, geothermal, wind, and solar. And we'll also touch on some others, or at least I'll give you links for some others. From there, we're going to look at the main issues that are facing us as we shift towards renewables. One is that we must update our electric grid. We touched on the electric grid in last lecture, and we're going to talk about the things that we need to do to update it to accommodate renewables. And the other main issue is many of our renewables, at least our two big ones going into the future, or at least right now, wind and solar, are not on demand, essentially meaning that they are subject to volatility. The sun doesn't always shine, the wind doesn't always blow. So during those instances, there could be cases where we have a mass need or demand of energy and it's maybe cloudy outside. So how do we address that? And one of the ways is to utilize energy storage, which there are a bunch of new technologies that are coming out to better address that. And then after that, we are going to discuss alternative fuels, right? It's not just electricity that is important, that it's important that we become more environmentally friendly with, but we also need to address fuels and fuel sources, right? Get away from oil as that primary fuel source, or look for more carbon neutral or green fuel sources. We're going to start by looking at hydroelectric or hydropower, and I have a video for you guys to watch.
Hydropower. Hydropower, or hydroelectricity, refers to the conversion of energy from flowing water into electricity. It is considered a renewable energy source because the water cycle is constantly renewed by the sun. One of the first uses of hydroenergy was for mechanical milling, such as grinding grains. But today, modern hydro plants produce electricity using turbines and generators. The mechanical energy created by moving water spins rotors on a turbine. This turbine is connected to an electromagnetic generator which produces electricity when the turbine spins. There are two main types of hydroelectricity production, dams and run-of-river. Hydro dams utilize the potential energy from dammed water to produce electricity. A dam is a large barrier constructed to raise the level of water and control its flow. The elevation created by the dam creates gravitational force for turning the turbine when water is released. Some dams also contain an additional reservoir at their base where water is stored to be pumped to the higher reservoir for release when electricity is in demand. This is referred to as pumped storage hydro. The second form of hydroelectricity production is run-of-river hydro. Run-of-river still uses turbines and generators, but relies on natural water flow rates of rivers, diverting just a portion of the water through turbines. Because run-of-river hydro is subject to natural water variability, it is more intermittent than dammed hydro. There are various sizes of hydro plants that produce electricity. Large hydro, greater than 30 megawatts, small hydro, 100 kilowatts to 30 megawatts, and micro hydro, less than 100 kilowatts. The Hoover Dam in the United States is a whopping 2,074 megawatts, which is enough to serve 1.3 million people. Of all renewable energy sources, hydropower holds the largest share of worldwide electricity production. Hydropower has several benefits. It is a cost-competitive form of electricity, even though the initial building cost can be high. It is quite reliable compared to other renewable options and pairs well with other sources as it can be used as baseload power. In some cases, dammed reservoirs can also help with flood control and be a reliable water supply for communities. There are also some concerns with hydropower, especially when it comes to large dams. Damming a river has a major impact on the local environment, changing wildlife habitats, blocking fish passage, and often forcing people in riverside communities to move out of their homes. In addition, dam failures can be catastrophic, claiming the lives of those living downstream. Hydro plants are also not completely free of greenhouse gas emissions. As with most forms of energy, carbon dioxide emissions happen during construction, particularly due to the large quantities of cement used, and plant matter in the flooded areas makes methane, another greenhouse gas, as it decays underwater. That's hydropower.
Okay, so I thought that was a really good overview of hydropower or hydroelectric power. A couple things to note, right? Essentially how it works, and this is going to be common through many of these methods, is that whole idea of to create electricity, that electrical generator, right? It's just, as you recall from the last lecture, it's moving magnets in that magnetic field, and that creates that electrical current. And all these techniques, or at least a majority of them, except for solar, are just different ways that we are coming up with spinning a turbine to spin that rotor to create that motion in that magnetic field to create an electric current. Right, you're going to see it with all of these. We already saw it with coal and natural gas and nuclear. And with, like I said, a majority of these renewables, it's the same idea. We just need to come up with ways of spinning that turbine to create electricity. So as the video mentioned, it's a couple of years old when this video was produced. So currently, hydropower in the U.S. accounts for about 7% of the total U.S. energy production. I think it was just surpassed by wind. So wind is a little bit higher now. Most of the plants that were built in the U.S. were built before 1990. Going forward, hydropower is not, it's not likely that we're going to see an increase in large-scale production of these hydropower facilities, mainly because of those environmental impacts that they touched on in the video, right? There are very large impacts for damming a river, both upriver and downriver, affecting habitat, land use, wildlife populations, fish passage, etc. So there's a lot of impacts to this, and we're kind of going away from those techniques. Where we may see stuff is increasing capacity at existing dams, adding those smaller run-of-river projects, right, that take a part of that river and run water through it. We are seeing technological advances in some of the turbines that are becoming more friendly to fish passage, etc. So that's really what we're going to see hydropower in the U.S., right? Kind of an increase or better efficiency at existing plants, maybe some smaller run-of-river plants, river projects as well. That's not worldwide, right? There are still large-scale dams that are being built in Brazil and China, but in U.S., it's not likely that this is going to be a main focus of renewable power going forward, at least large scale. Oh, how do I get back to? No, get me back to my presentation.
Hydro.
Oh, there we go. Okay. So next, we're going to look at biomass.
Renewable
Oops, sorry.
Energy 101. Biomass, the original renewable energy. It's been part of our lives since our ancestors learned to control fire. In fact, it's made possible by the sun, whose energy is absorbed by trees and plants through photosynthesis, and then released when organic matter is burned or decomposes. First, there's plant waste. Wood scraps, sawdust, and crop waste can be collected from farms or manufacturers. The waste is burned to heat water. The hot water creates steam. The pressure of the steam spins a turbine. The turbine powers a generator. The generator creates electricity. Simple, really. Next up, animal waste, also known as the problem of cow poop. The solution? Waste from farm animals can be collected in a large tank called a digester, filled with bacteria that eats the waste and converts it to methane gas. The methane is captured and burned to heat water and create steam. Sound familiar? Second verse, same as the first. This same principle can also be used to capture methane, a potent greenhouse gas with 25 times the heat-trapping ability of carbon dioxide, from landfills. Once a section of the landfill is closed off, pipes are run from the waste to collect the gas, which can then be burned to make electricity or heat. Biomass may not be the prettiest form of renewable energy, and it needs to be used carefully and thoughtfully to protect ecosystems and prevent greenhouse gas emissions. But it can be a smart way to make use of waste. Power to the poop.
Okay, so biomass. Again, very similar parallels with the things that we've seen before, right? This is just essentially a different fuel source, same type of process, right? So instead of burning coal, we're burning waste, vegetable matter, wood, etc. Now, biomass currently in the U.S., at least in 2020, was about 1.4% of our total U.S. energy production, so not a whole ton. The carbon neutrality and the environmental friendliness of this technique is debated, and it really depends on your crop and land management, right? So if we are cutting down forests to be used for biomass, that's maybe not the best method or the most environmentally friendly method. But this is, I think, a really good way of utilizing different waste streams, right? So we produce a lot of waste in this country, and this could be a way of taking that waste that would otherwise just go to a landfill and utilizing it to create energy. Right now, we're still burning things, so we're still going to emit other air pollutants, right? That we see with burning other carbons, fossil fuels being, carbon-based. But if we do this smartly and thoughtfully, as they said, this is a more environmentally friendly and could be a carbon neutral process of generating electricity. No. And here's a quick video. We'll watch it real fast of, like I talked about, I think where we see a real benefit, or could see a real benefit with biomass, is for recycling and waste management. And here's just a little
A renewable
example of
called
that.
biomass generates less than 2%. Harvesting it, moving it, storing it, making sure it produces a consistent amount of energy, those have been ongoing challenges for scientists looking to use biomass. But the biomass industry is hoping to change that.
There's so many non-utilized waste streams in this world. We have food waste, we have transportation waste. There are endless amounts of byproducts that are currently not utilized.
What if you could power your home and live completely off the grid by just using your own trash? Each year, over 1 billion tons of solid waste is produced globally. That's expected to double by 2025. And of the 8.3 billion metric tons of plastic produced worldwide, only 9% is recycled. But to this German startup, our trash is their treasure.
The initial vision that we had was to build a power plant that is truly mobile, that it can convert all the waste and turn it into clean energy right on site.
Entrade's power plants can fit entirely inside a 20-foot shipping container and mainly run on biomass. Biomass is a renewable organic resource that comes from plants and animals and can be turned into fuel. Ulig and his team work to identify local waste streams. Anything from manure to discarded lumber to yard trimmings, and even peanut shells can do the trick.
We crush it, we dry it, and then we pelletize it.
These biomass pellets are what Entrade's power units run on. The company has also developed the technology to use non-organic waste as fuel. By taking plastic that would otherwise end up in landfills and combining it with other green waste, they claim their units can produce enough electricity to power homes, neighborhoods, and factories.
And then we put it into our reactor, and it only stays there for a few seconds before it totally converts into a natural gas replacement.
It's a process called gasification. When plastic goes into a small reactor, it burns at extremely high temperatures, breaking down its polluting particles. The result? A hot gas that is then used to create electricity. Entrade sees potential in countries dealing with large amounts of plastic pollution. But figuring out the right mixture of plastic and biomass can be complicated and is still being tested. The company wants to take their mobile power units one step further. Their newest unit is a mini power plant about the size of a fridge.
We were always thinking of this power unit you can bring to the middle of nowhere, plug it in, use all the waste you find around it, pelletize it, and you have a complete power supply on site. And I can see many people in farmhouses all over the world just putting this next to their kitchen and generating their own power from the waste that they're currently throwing away.
But are these mini units as easy to use as they seem?
If you look at the bags of pellets that we produce here, we need about 2 to 3 bags per day. So you can actually fill it by hand in the morning, have a complete power supply around the clock.
That's a lot of pellets. Entrade's off-the-grid vision is still in its early phases. Questions like how much energy it would take for someone to actually make these pellets at home still remain. The company envisions communities combining their green waste and making their own biomass fuel. And they're also working to make these things affordable.
The 50 kilowatt unit that you find in a big container was initially about $5 million to build. We have brought this down to a retail price of $250,000. As the production numbers go up, we think we can offer this for the price of a small car.
Entrade hopes that mini power plants like these could change the way cities and towns source their electricity, making them self-sustaining, and in some cases, cleaner.
You're going to have communities processing their own waste using its electricity, and it's totally going to revolutionize the way we're going to live.
Kind of neat, right? So I thought that was cool. Again, I think as they kind of touch on, I think where biomass could be really great is as this waste management process or technique. And really what you see here is starts to touch on why we need to update our grid. Where most people involved in energy, scientists, policymakers, etc., where they see things going in the future with energy is instead of having our current system where we have these large-scale power plants that are producing the majority of our energy and our electricity, and then that's getting distributed, we're going to have more of these smaller little microgrids, right? So we'll have smaller towns or areas that have smaller generating stations, like something that you might see with that small biomass reactor that they were talking about that maybe a community has, that is local and produces local energy. And those are all going to be linked together as part of this larger grid. So that's where we see things going, or at least many people see things going in the future, and it's why we're going to need to update our grid to accommodate all these smaller energy sources or energy generating stations. So that's biomass. Maybe by the end I would figure out that I need to click first and then go. Okay. Next, we are going to look at geothermal, right? And as you're seeing, I've got videos for all of these. I tried to keep them short because I don't want this going too long, but I think they're good ways to actually see the process.
You may have relaxed in a natural hot springs pool, or seen the old faithful geyser blasting hot water into the air in Yellowstone National Park. But have you ever thought of where all that heat comes from? Well, it comes from deep beneath the surface of the Earth, and it's called geothermal energy. And we can use it to generate clean, renewable electricity. Okay, here's how geothermal works. Heat from the Earth's crust warms water that has seeped into underground reservoirs. In some places, when water becomes hot enough, it can break through the Earth's surface as steam or hot water. This usually happens where the Earth's crust, or plates, meet and shift. In the past, taking advantage of geothermal energy was limited to areas where hot water flowed near the surface. But as geothermal technologies advance, we can leverage even more of these natural, renewable energy sources. Engineers have developed a few different ways to produce power from geothermal wells drilled into the ground. Have a look at this. It's a dry steam geothermal power plant, and it's the most common type of geothermal technology used today. Underground steam flows directly to a turbine to drive a generator that produces electricity. Pretty straightforward. Another geothermal technology is called a flash steam power plant. A pump pushes hot fluid into a tank at the surface, where it cools. As it cools, the fluid flashes, or quickly turns into vapor. The vapor then drives a turbine and powers a generator. A binary cycle plant works differently. It uses two types of fluid. Hot fluid from underground heats a second fluid, called a heat transfer fluid, in a giant heat exchanger. The second fluid has a much lower boiling point than the first fluid, and so it flashes into vapor at a lower temperature. When the second fluid flashes, it spins a turbine that drives a generator. The environmental benefits of this clean, round-the-clock, renewable energy source are substantial. Low emissions, small physical footprint, and minimal environmental impact. The few byproducts that can come up are often re-injected underground. Geothermal energy can also help recycle wastewater. In California, wastewater from the city of Santa Rosa is injected into the ground to generate more geothermal energy. Some plants do produce solid waste, but that solid waste may contain minerals that we can remove and sell, which lowers the cost of this energy source. The U.S. Geological Survey estimates that untapped geothermal resources in the United States, if developed, could supply the equivalent of 10% of today's energy needs and cut our dependence on fossil fuels. In fact, electricity generated by geothermal energy already provides about 60% of the power along the Northern California coast, from the Golden Gate Bridge to the Oregon state line. Geothermal energy, helping to push America toward energy independence and a clean, renewable way to meet our growing energy demands.
Okay, so that's geothermal. And again, same idea, right? We just need to create steam, or we need to turn that turbine in one way or another. Now, with geothermal, instead of actually burning materials, burning fossil fuels, or burning biomass, we're using the natural heat of the earth to create that steam, to spin that turbine. I think it's a really neat form of energy generation. It was first built, the first geothermal generator was built in Italy in 1904, and it was able to power 5 light bulbs. So there's been a great increase in the ability of this technique to create energy since that first generator back in the early 1900s. And this is, like they said, in California, it is used widely in certain areas. In Iceland, they're probably the most well known for their geothermal energy. So Iceland uses geothermal, and that accounts for about 30% of their electricity generation and 90% of their residential heating. They really went kind of all in and promoted this method really following the 1970s. So before they decided to switch or go for geothermal, they were primarily fossil fuel based and oil based, and there was an oil shortage in the 70s where they couldn't get any to Iceland. It was worldwide oil shortage. Iceland couldn't get any oil, and they realized they needed to shift their processes and how they went about creating energy. And they decided to go geothermal, like taking advantage of the natural geology in the area. And it's been a great success, right? Like I said, they are well known for producing geothermal energy. One of the big benefits of geothermal is that it's on demand, right? That important aspect that we can ramp up production when we need to, or decrease production when we need to. We're not dependent on other external factors, such as the amount of sunlight or the amount of wind that is blowing. The real main problem with geothermal is that it takes years to develop and there are high initial costs, right? So to develop a geothermal plant, there is a lot of initial drilling that needs to be done, exploratory drilling to find the best spots to develop it. There's all these upfront costs that that need to be paid. And years that go into building this plant before it's actually functioning. Once it's functioning, it's super efficient. It makes you get a good return on your investment. It starts making a lot of money, but that initial cost is really high, and because of that, it's not always super attractive to investors. There are some rare cases where this process could trigger some small earthquakes due to the drilling that is happening to produce them and then starting that steam removal, but apparently it's very, very rare. And like that video said, this could be a method that could supply up to 10% of U.S. energy needs. So a significant amount of energy can be produced using geothermal. Right now, we've only tapped a small portion of it, and only about 0.43% of our energy is produced via geothermal. But I think this is a real good, viable method in the future that we can explore, right? And it's going to depend on location, right? Out west is going to be our best areas for geothermal, and that has to do with plate tectonics, as they mentioned in the video, right? Areas where those plates are close together, or edges of plates are close together, are going to be ideal for this geothermal power. Yeah. Okay, that is bringing us to wind and solar, probably the two ones that you think of the most when you think about renewables. So we'll watch a short video with each of them, and we'll talk a little bit more about them afterwards.
Every 24 hours, wind generates enough kinetic energy to produce roughly 35 times more electricity than humanity uses each day. And unlike coal or oil, this resource is totally renewed each day. So how can we harness this incredible amount of energy? And is it possible to create a world powered entirely by wind? The basic principle of wind energy is simple. A series of sails or blades mounted around a rotor catch the wind and translate its kinetic energy into rotational energy. Traditional windmills use that rotational energy to grind wheat or pump water. But in modern wind turbines, it turns a generator that creates electricity. This conversion from wind to rotational energy to electricity has defined wind turbines since their invention in the late 19th century. And there are three primary factors that determine just how much energy they can produce: the size and orientation of the blades aerodynamic design, and the amount of wind turning the rotor. First up, blade orientation. Wind turbines can be designed with their rotor on a vertical axis or a horizontal axis. Vertical blades can pick up wind coming from any direction, but with much less efficiency than horizontal axis rotors. Horizontal designs allow blades to capture the wind's full force by tracking the wind's direction and turning to face it. This turning process is called yawing, and older windmills achieved it through manual monitoring. Today, wind sensors and computer systems automatically adjust the blades with expert precision to capture as much energy as possible. Outside rotor orientation, the blades themselves need to be shaped to maximize efficiency. While early designs used flat blades, modern blades are curved like airplane wings. Wind travels faster over the curved surface, creating a low-pressure pocket above the blade that forces it upwards. Since the amount of lift depends on the angle at which the wind is moving relative to the blade, modern blades also incorporate a twist, optimizing how much of the blade can cut into the wind. Made of fiberglass and resin layers, these blades are strong enough to operate through rain, lightning, and blistering sunlight for over 20 years. Even with aerodynamic blades and a horizontal rotor, a wind turbine can only capture wind if it's in a windy environment. Wind speeds typically increase the higher into the atmosphere you travel. So today, most turbines are well over 100 meters tall, with equally large rotor diameters. A turbine of this height and size can capture a huge amount of wind, generating enough electricity every year to power 750 American homes. A wind farm of 200 similarly sized turbines could power over 150,000 American homes, or twice as many European homes, for an entire year. Offshore wind farms contain an even greater number of even larger turbines. In 2019, the largest wind turbine ever built began operating off the coast of the Netherlands. With a rotor diameter of 220 meters, just one of these turbines can meet the annual power needs of 16,000 European households. Despite its amazing potential, wind energy still faces challenges. Wind may be a free and unlimited fuel, but no matter how large or efficient a turbine is, there's a mathematical limit to how much wind it can convert into electricity. German physicist Albert Betz calculated that since some wind must remain to keep the blades spinning, a turbine can only ever capture 59.3% of the wind's energy. Additionally, some people feel turbines disrupt natural scenery, and wind energy's intermittent availability can make it difficult to integrate into electrical grids. But even with these challenges, modern wind turbines have made wind energy the most efficient and inexpensive source of electricity. Wind turbines already provide essential energy for communities around the world, and for many farmers, hosting a wind turbine can be a reliable source of additional income. With continued improvements in wind forecasting, electrical grid infrastructure, and energy storage, wind power might blow away all our energy problems. Next up, learn how solar...
Okay, so that's wind. It is the fastest growing energy source in the world, right? And for good reasons that were touched on in that video. It is clean, right? There are no emissions associated with wind power, and it's cheap. Right, the costs of wind have decreased dramatically. It's the cost of developing a wind farm is about half the cost of building a natural gas plant. So it's cheaper than all these other sources of energy generation. And because of that, we are seeing this huge increase in wind development. In 2020, in the U.S., wind generated about 8.4% of our energy capacity, or about 337.5 billion kilowatt hours. Only 20 years ago, that number was 5.6 billion. So a huge increase in the amount of wind and the electricity that we're generating through wind. Another benefit, as they touched on, besides it being clean and cheap, right? It also can be a source of income, especially for rural areas. If you look at possible wind and solar locations, a lot of them are out in the Midwest here, right? Traditional farm country. Well, here's an additional resource or form of income now. If you can utilize some of your land for and lease it for these wind projects, it'll generate extra income for you. And in fact, in 2021, wind energy generated $706 million in land lease payments to rural landowners, right? So another advantage of wind. And if you see here in these possible locations, you see off along the Jersey Shore and really this mid-Atlantic area, huge location for offshore wind. In your homework, I'm having you reading an article about offshore wind in New Jersey. There's a large push for offshore wind. We're going to start seeing it being developed in the next couple of years as we try and transition to this carbon neutral, more environmental friendly energy. So wind, you're going to see it living in New Jersey. You are going to be aware of it because we are installing wind farms offshore. Now, the main problem of wind energy, right, is that it's not on demand, as we've kind of touched on already. The wind doesn't always blow. There are going to be times where it's very windy and you produce extra energy. So what do you do during those situations? And one of the big things is that we need to develop some sort of energy storage option that would really take this to the next level. There are also some environmental effects that we need to be aware of. We know that this can impact birds and bats. However, there are steps that we can take to mitigate this, right? Particularly with bats, they found that most of the impacts or bats were most active during these low windy occasions, and they were able to adjust how they operated their turbines to reduce impacts to bats and mortality to bats. Same things they can adjust as we study these in relation to birds and other populations. And there are also potential impact to marine life when we're talking about those offshore wind farms. So we do need to be careful in how we place these, where we place them, and monitor to ensure that we're not having too drastic of effects when we install them. But despite those potential impacts and those potential environmental impacts, the benefit that wind can provide in terms of this clean energy source is huge. And we're going to see this only increase in the future. And that is going to bring us to
solar energy works.
To our last renewable, solar, right? And also probably right behind wind in terms of growth. Before we watch the video, I'll just touch briefly, right? It accounted for about 8.4% of our, oh, that's still the wind. That should be changed. I'll have to look it up and tell you how much electric accounted for our, oh, this is correct. It's just the 8.4% is wrong. Oh, no, I can't change it while I'm on here. Okay. So in the US, solar power or solar photovoltaic power generated 90.9 billion kilowatt hours of electricity. I'm not sure what percentage that is. But again, this is a big increase compared to only a couple of years ago, right? In 2010, so only about 10 years ago, we only produced 1.2 billion. And going back 20 years ago, it was about 0.5. So this is rapidly growing, just like wind. This is a rapidly growing energy source. So let's watch our video, and then I'll touch on a couple more things.
The Earth intercepts a lot of solar power, 173,000 terawatts. That's 10,000 times more power than the planet's population uses. So is it possible that one day the world could be completely reliant on solar energy? To answer that question, we first need to examine how solar panels convert solar energy to electrical energy. Solar panels are made up of smaller units called solar cells. The most common solar cells are made from silicon, a semiconductor that is the second most abundant element on Earth. In a solar cell, crystalline silicon is sandwiched between conductive layers. Each silicon atom is connected to its neighbors by 4 strong bonds, which keep the electrons in place so no current can flow. Here's the key. A silicon solar cell uses 2 different layers of silicon. An N-type silicon has extra electrons, and P-type silicon has extra spaces for electrons, called holes. Where the 2 types of silicon meet, electrons can wander across the p-n junction, leaving a positive charge on one side and creating negative charge on the other. You can think of light as the flow of tiny particles called photons shooting out from the sun. When one of these photons strikes the silicon cell with enough energy, it can knock an electron from its bond, leaving a hole. The negatively charged electron and location of the positively charged hole are now free to move around. But because of the electric field at the p-n junction, they'll only go one way. The electron is drawn to the n side, while the hole is drawn to the p side. The mobile electrons are collected by thin metal fingers at the top of the cell. From there, they flow through an external circuit, doing electrical work like powering a light bulb, before returning through the conductive aluminum sheet on the back. Each silicon cell only puts out half a volt, but you can string them together in modules to get more power. 12 photovoltaic cells are enough to charge a cell phone, while it takes many modules to power an entire house. Electrons are the only moving parts in a solar cell, and they all go back where they came from. There's nothing to get worn out or used up, so solar cells can last for decades. So what's stopping us from being completely reliant on solar power? There are political factors at play, not to mention businesses that lobby to maintain the status quo. But for now, let's focus on the physical and logistical challenges. And the most obvious of those is that solar energy is unevenly distributed across the planet. Some areas are sunnier than others. It's also inconsistent. Less solar energy is available on cloudy days or at night. So a total reliance would require efficient ways to get electricity from sunny spots to cloudy ones, and effective storage of energy. The efficiency of the cell itself is a challenge too. If sunlight is reflected instead of absorbed, or if dislodged electrons fall back into a hole before going through the circuit, that photon's energy is lost. The most efficient solar cell yet still only converts 46% of the available sunlight to electricity, and most commercial systems are currently 15 to 20% efficient. In spite of these limitations, it actually would be possible to power the entire world with today's solar technology. We'd need the funding to build the infrastructure and a good deal of space. Estimates range from tens to hundreds of thousands of square miles. Which seems like a lot, but the Sahara Desert alone is over 3 million square miles in area. Meanwhile, solar cells are getting better, cheaper, and are competing with electricity from the grid. And innovations like floating solar farms may change the landscape entirely. Thought experiments aside, there's the fact that over 1 billion people don't have access to a reliable electric grid, especially in developing countries, many of which are sunny. So in places like that, solar energy is already much cheaper and safer than available alternatives like kerosene. For, say, Finland or Seattle, though, effective solar energy may still be a little way off.
All right, so that's solar. So I wanted to show that one, and I saved it for last because this is a different type of electricity generation, right? Almost all the other ones were that electromagnetic induction. We needed something to turn that turbine, to spin that rotor, to create that magnetic field, to create that electric current. This is different, right? It's a different process. This is something, it's a little more akin to like how a battery works. So just something to be aware of, right? Now, as they mentioned, and as we kind of talked about, solar is a great option going forward, right? It is clean, no emissions, it is cheap. The price of solar has drastically declined since 2010, right? It's the price of solar energy has declined by about 89%. It's now cheaper than our fossil fuel-based forms of electricity as a result, right? And we've seen this huge increase in solar consequently. The big rub against solar, as they mentioned in the video, right, is that it's not on demand, and we have those issues with Not every place is sunny, or you could have a cloudy day. And as a result, you need a system that's able to either transport that electricity from those sunny areas to those cloudy areas, and that better storage options that we've touched on already a couple of times. There are some concerns with loss of habitat, right? You do require space, perhaps more space with solar than wind, right? If you install those wind turbines, you can still utilize the land underneath them. You can't do that with solar. But we can mitigate for this by building on lower quality land, land that can't be used for other things, such as brownfield sites that are historically contaminated by toxins or toxic materials. We can still build solar on that and utilize that land. There's also a concern that the manufacturing process of the solar panels or solar cells does involve some hazardous materials, so that's something to be aware of as well. But again, despite these things, solar is a good option going forward, and it's going to continue to increase. I use solar panels not on my house, but I use them for work. We have a bunch of equipment that we need to power out in the field, and I've hooked up solar panels to that equipment to utilize that as energy instead of using batteries or trying to run electric or anything like that. So really great option going forward. Yeah. Okay, which brings us to a couple other of renewables. We're not going to go through these, but I have links here for you guys to check all these out if you're interested. Again, these are things that may be a part of our energy systems in the future. Tidal power, right? Utilizing the tides to generate electricity. Human energy, kind of an interesting one. Nuclear fusion. Something in the future that could be a game changer, or at least they've been touting for years and years and years. And either kind of funky aspects of solar. They mentioned those floating solar farms, but how about a space-based solar system? Right, so all potential things in the future. As we see with all of these renewables, and as we're going to look when we get into some of the batteries and storage technologies, there is lots of opportunities for different types of renewables and different types of technologies going forward. And it's going to be interesting to see what works, right? And what wins, right? Where do we go? What technologies do we settle on? It's a lot of opportunity in the future for anyone interested in this field. So we kind of, with that, went through the main types of renewable energy, right? Now we're going to briefly talk about some of their issues, and it's stuff we've already built, we've already talked about, right? We have to update our electric grid to accommodate these renewables, and we need energy storage. So if we're talking about our grid, right, we already talked about what our grid was in the last lecture. Some of the issues with it is that it's old, right? Our grid, much of our grid was constructed in the 50s and 60s, and it was designed around that traditional way of generating electricity at a power plant, particularly a coal power plant or, natural gas nowadays. So having these large-scale utilities that are generating electricity and then being transported to homes. But because that grid was designed for fossil fuels primarily, it's not designed for the volatility that we see in wind and solar, right? So the wind and solar, it's more volatile. When it's very sunny, we're producing more energy. When it's very windy, we're producing more, and vice versa when it's not as sunny or not as windy. So this power grid isn't designed for that. It's not easy. There's not quick ways to shuttle around energy where it's needed. And it's also not designed for the increase in electrical usage that we're seeing nowadays or into the future, right? We have more devices. We have cars that are running on electricity. So there's a greater demand of electricity upon the grid. And the grid isn't designed to address these new renewable sources that are being incorporated into it. So we need to update our grid, right? And likely what our grid in the future is going to be that type of hybrid grid that I already kind of talked about, right? So it's not just these several large generating stations, but we're going to have these microgrids that are these smaller electrical generating stations that are localized to a certain area, and they're providing electricity to that local area, but then they're also hooked up to this larger grid. And as part of that, our grid needs to be smarter, right? So we need to adapt sensors and technology that can better accommodate the volatility that we talked about, both in our energy generation and in our energy demand, right? So right now, instead of having humans having to switch things to transfer lines and energy, we could have sensors and artificial intelligence that can do this for us in a much faster and more efficient way. We also need to update just some of that infrastructure in the terms of transmission lines, right? We need better, improved transmission lines that are able to carry this extra renewable capacity. If we go back a couple slides where we talked about wind energy, a lot of that potential wind energy is out here in the Midwest, away from these dense population centers. Most of our dense population is found along the coasts. So if we're generating electricity here, we need to have these efficient lines that are able to take that electricity from the middle of the country and transmit it efficiently to the coasts. So all this is going to cost a lot of money. It's estimated about $2.5 trillion over the next decade to do all of this, which is a lot. But if you think about the need for this and how much better things would be with this grid, it is worth that investment. So power grid, we need to update our power grid. We also need to update our energy storage, right? That was one of the things we saw with a lot of these is that, especially wind and solar, right? There are times where we can produce a lot of energy. And if we have a way to store that energy, we could then utilize it during these times when the wind isn't blowing or the sun isn't shining. So currently, 96% of our energy storage comes from pumped hydro, which that video talked about. Right, and this is where during you have extra energy, you pump water essentially uphill, and then when you need that, you release that water, it flows through, spins a turbine, and produces your excess energy, energy when you need it. The problem with pumped hydro, right, it requires a lot of land. You need to create this whole separate system up here and down here, these reservoirs. It disrupts the environment, and this is only really functional in certain areas where the environment is suitable for this. So we need different and new energy storage. So there's a number of methods in the future. And just like with renewables, it's going to be interesting to see which one of these methods takes off. So there are gravity-based storage. It's the same idea as this pumped hydro, where we are using gravity to create this energy when we need it. But in this instance, there's a company, Energy Vault. Instead of using water and pumping water, they use excess energy during these very sunny times or very windy times to raise blocks in this large tower that you see here. And they raise these bricks up, and this is automated, and it's done by artificial intelligence, which brick and where to put it. And then when they need electricity, they drop those bricks, and that's going to create the excess energy that they need. This is a large utility scale storage. So this is for storing a lot of energy. And in fact, one of these can store about 350 megawatts or enough to power 40,000 homes for 24 hours. So these are large scale things. You can build multiple of them in an area. And these are more suitable in areas worldwide, right? So you don't need a specific system where you have water in an area or reservoir. You can just build these in locations where you don't need water. This is, something in the future. We don't know. Maybe this is going to take off as a method. Maybe it's not. Besides gravity-based storage, we have chemical-based storage. Right? These are batteries. I have a real good video that'll look at show you how batteries work if you guys are interested in that. But currently, our main battery or our best battery are those lithium-ion batteries. The problem is they're too expensive for these large-scale grid applications, right? So to have enough batteries to store energy that we can use for a large section of our grid, it's too costly, right? And there's also some issues of fire associated with them as well. So we knew if we want to go with chemical-based storage, if we want to go with batteries, we need new batteries that are cheaper and more efficient. So there are other types of batteries that are being developed. A subset of them are these flow batteries, which don't have fire issues that you may see with lithium ion. They don't have capacity fade. So a problem with lithium ion is that over time they lose their capacity. And we don't see that with these flow batteries. But we still have issues with storage and the ultimate amount of capacity, right? So where batteries are likely going to be are on these smaller scale systems, right? These may be microgrid systems or these local systems that utilize that need that storage, maybe not a large utility scale. And then we have thermal-based storage. So this is another different type of storage that we may see in the future. And what's happening here is that we have excess electricity is used to heat up materials, these carbon blocks. And then when needed, that heat from those carbon blocks is converted back into electricity using a heat engine. Now, traditionally, that would be like a regular type of steam engine, but there are new advances in solar cells that are able to capture the light radiating from these blocks and convert that into electricity, right? So again, a different option that we may have in the future for energy storage. And if you guys are interested, here's a YouTube video down here that goes a little more in depth into each of these options and some different companies and their techniques within each of them. So, like I said in the beginning, we don't know which way this is, what's going to work, right? All of them have advantages and disadvantages, and we're going to see going forward into the future what is really going to take off as this really good energy storage option. We're going to end by looking at fuel alternatives, right? That whole part was electricity, but again, it's not just electricity that we need to be aware of or concerned with. We have to be concerned with other forms of energy generation, particularly fuel that we use for vehicles, right? That's a large portion of the energy that we consume. It's a large portion of emissions that are produced. So if we are serious about addressing climate change and emissions, we need to look at fuel alternatives that are more environmentally friendly. So we have a couple different options, right? One of which is to create hydrocarbons using carbon dioxide and water, right? So instead of taking our hydrocarbons from the earth, right, pumping for oil, we can create hydrocarbons from existing carbon dioxide that is in the atmosphere. And we can fuel this process using renewable energy. So this way, we are essentially carbon neutral, right? Because we're taking carbon dioxide from the atmosphere, we're using it to create a fuel, and then that is getting burnt off, and that carbon dioxide is getting released back into it. But it's a cycle, right? So what we are taking in, we're then emitting, carbon neutral. This would still, we would still likely have other types of emissions with this process, but in terms of addressing carbon dioxide, this would be a neutral way of going about fuel alternatives. And there are many people who are looking to do this and trying to figure out ways to do this. Another fuel alternative could be green hydrogen, right? So we talked about energy storage, right? And a problem with energy storage with wind turbines. Well, one way we can get around this or utilize that excess energy or that excess electricity that's being produced during these really windy days is to produce a different type of fuel. So we can attach electrolyzers to marine wind turbines. And during these periods of excess energy, that electrolyzer is able to break water down into its component parts, oxygen and hydrogen. And then we can store that hydrogen as fuel, right? And that hydrogen fuel could be used to replace fossil fuels. So it could be used to power cars, vehicles, boats, planes, etc., and it could be used to heat homes, right? So here is a really good way of utilizing that times of excess wind energy to create a fuel that can again be used in other applications. And they are experimenting with this and developing different vehicles now that are running on hydrogen. And this could be something in the future. And then there's also second generation biofuels, right? So other biofuels or fuels that are being made from different materials, right? People are experimenting with algae, taking municipal waste and making biofuels, from perennial grasses. So these are grasses that grow each year, right? More of an environmental friendly than alternative than our first generation biofuels, which were primarily like corn based, right? So again, different options in the future going forward, and it's actually exciting to see what is going to be the one that takes off, and it's likely won't just be one, right? I think the future is going to be a lot more diverse in terms of our energy generation and our fuel alternatives. I think there are a place in the markets for all of these, and it'll be really neat to see how that turns out. So that is it for renewables. I hope you guys are doing well, and I will see you at the next lecture.